In this first part of Module 5, or the lecture from Module 5, we're going to reintroduce the idea of clustering. If we look at where we are in the overall course, we're still focused in this third area about data mining algorithms for clustering, and we'll use this as we springboard forward into other areas for extracting insights for number 4. So where we've been so far in terms of Module 2 on graph analysis, Module 3 on distance measures and these kinds of things, we now have abilities to identify graphs, construct them from our data, identify communities in some sense or groups in these graphs in some sense. We have ways to evaluate how similar 2 points are in a more general sort of space that's not necessarily graph oriented. And now we want to be able to sort of unify all of this. We can generate clusters not just in graphs, but also in this general space where we can evaluate distance. So how do we generate clusters in a more general way? So that's what we're going to talk about today, or in this first week of the Module 5 lecture. We'll talk about comparing and contrasting two approaches for hierarchical clustering, describing how we represent a cluster that is composed of potentially multiple points, how we evaluate distances between clusters once we have them, and then when do we know when we should stop clustering. So recall that the main motivation that we've keep coming back to throughout the past several lectures is about we want to make the web more useful and informative, and a major way to do that is to have ways to group content on the web, whether it be documents, images, tweets, products, users or weblogs, all these different things. Ultimately, we have some idea of we have some goal of trying to group content here. And we've talked about clustering before to some degree when we talked about graph construction, when we talked about clustering versus partitioning. So in the general case, we've talked about clustering as identifying groups where objects in these groups are similar, where similar has some sort of real world meaning. And maybe we've specified K beforehand. If we were doing partitioning, maybe we haven't necessarily pre-specified K, or at least you can do clustering without having to specify K up front, though you definitely can. And we'll talk about that. So we'll return to this tired graph where we have a network of elements or objects in a data set, and the things or elements that are in the same cluster are similar in some sense, whether these are all things about Jaguar the car in this cluster on the top left, all things about Jaguar the operating system on the right, or all things about Jaguars the animals in the bottom. When somebody goes to Amazon and searches for a product and then selects some product that embeds them into a cluster, then we can extract elements from that cluster that are all likely to be similar and use those for recommendations or additional information that might help the consumer find new products of interest or new friends, new interests, these kinds of things. The motivation here, or rather the idea here, is that two nodes that are in the same cluster are likely to be way more similar to each other than two nodes in separate clusters. So this is the sort of underlying intuition that we have with clustering. So if we have one point here, we now know how we can evaluate that these 2 points are similar using the distance metrics from 2 weeks ago. And that lets us know that even if we can't necessarily plot this space, when we see a particular new point, we can evaluate distance between them and say, well, these 2 points potentially belong in the same cluster. So when we add new points, we can say these few points sort of help us generate or characterize some cluster. But the question is, how do we use this information to actually build these clusters? So how do we know that these points all do belong in the same cluster now that we can identify or calculate the similarity among them? So for this idea of making the web more useful or informative, we can look for clusters of entities or clusters of similar objects. We can evaluate the similarity, and we can use this similarity to actually extract the clusters from our list of data. So in Module 3, we talked about building these distance matrices that tell us how far two elements are, or any two elements are in our data set. Now we can use that information to build clusters. But how do we do that? So we talked about ways to quantify how similar things are, but there's not necessarily a clear answer about how we quantify similarity or distance. If your context is looking at objects and you want to evaluate similarity among sets of neighbors, that's going to give that's going to use one type of similarity metric. So Jacquard similarity there may be the most appropriate. Whereas if you're looking at SimRank column or SimRank vectors for a number of different nodes in a graph. Then you have a bunch of these real valued vectors. Maybe you want to use some other kind of distance metric like cosine similarity or Euclidean distance here. Or if you're using pages at the same topic, maybe you want to use shingling first to featureize this content, and then cosine similarity may be the most appropriate here. And we showed a number of different visualizations for this. So if you have some adjacency matrix characterizing this graph, you can look at the Euclidean distance between all pairs of points in this graph, the cosine distance, the Hamming distance, Jacquard distance, and the SimRank distance here. So we have different ways of evaluating similarity among objects. And this means for us, we can have different clusterings on the same data based on what your context is or what the distance metric you want to use is. So first, let's formally define the idea of clustering. So we're given some set of points, and we have chosen some distance metric, whatever distance metric that is for whatever context you have. So we want to look at the distance between, or be able to calculate or evaluate distance between points in this set. And the objective is to group all of these points into some k set of clusters, such that points in the same cluster are more similar to each other than they are to points in different clusters. So if you take a random point or two random points in different clusters, their similarity should be, in general, much lower than the similarity of 2 points within the same cluster. In the example that I've given you here, where we have a bunch of points in this two-dimensional space, actually clustering in 2 dimensions is a relatively easy process. You can do this just by visual inspection, and in fact, if you only had 2-dimensional data, clustering is really a trivially easy kind of problem. So if we have this clustering in 2 dimensions, we can do this relatively easily. We can identify outliers even relatively easily. But really, the vast majority of data that we will encounter, especially at web scale, is not going to be this 2-dimensional data. Most interesting data is, in fact, high-dimensional data. So as an example from last week, we talked about the DBLP bibliographic data set that matches authors to conferences, where we have, almost 500,000 authors, several thousand conferences. This is much higher dimensional data. Or if we're talking about images, if we want to do image recognition, so for instance, the fashion imness data set is a popular data set for doing image characterization, for what kind of clothing item are you looking at in an image, or the STL10 image recognition data set from Stanford, where you have a bunch of different objects in your images. Well, these images can all be high dimensional as well. So in some sense, one way to deal with or featureize images is to treat each pixel in the image as its own feature. And you can get around that using convolution, but still we're talking about high dimensional data. And I mentioned this last time that high dimensional spaces are problematic. So this review article from the Communications of the ACM is, I think, a great place to read about this from Professor Domingos, that ultimately in high dimensions, distance starts to break down because almost all points are about equidistant from each other when you're talking about hundreds to thousands of dimensions. When we're looking at these images, clustering becomes harder. Now, one way we could do this is to apply what we learned from Module 4 about dimensionality reduction and take these images and project them into a low dimensional space. And we can do that. That's a perfectly reasonable way to do clustering. But then we start to see lots of overlap in the clusters or where objects may be in these clusters. This opens up a question about, well, do you cluster in the full space? Do you cluster in the lowest possible space, some 2-dimensional space where clustering is easy? Do you cluster in some intermediate space that's defined by SVD? Or across some core set of components through PCA or something like that? We want a general method for clustering that can work even in high dimensions. How do we develop a clustering that'll work in a general number of dimensions? So we'll talk about this by first introducing 2 methods of clustering. We'll introduce and talk about primarily in this lecture the idea of hierarchical clustering, which itself also has 2 subtypes. There's first agglomerative clustering, which is basically this bottom-up approach where you start with every point in its own cluster, and repeatedly through a number of different iterations, we combine 2 clusters that are nearest to each other in some way. So you take the 2 closest clusters to each other, combine them up into a new cluster, and repeat the whole process. So some visualization, this visualization here is called a dendrogram. We'll talk about that more in a few minutes, where you start off with every node is an individual leaf for its own cluster, and then you merge up the tree to generate this hierarchical clustering structure. But that's not the only way. You can also go from the top down, the divisive hierarchical clustering approach, where you start initially with all points in one cluster, and you recursively split this cluster up until you have some pre-specified number of clusters where you hit some stopping condition in your recursion. So that's the hierarchical method. There's also the point assignment method, where you have some set of clusters associated with some set of points, and then as new points come in, or as you evaluate new points, you assign points to their nearest cluster. So then you don't necessarily end up with this hierarchy of points. You end up instead with a much flatter assignment of these points are associated with this cluster, or this cluster contains these points. Something like what we've talked about, or what you may think about when you think of clustering in the general case. We've seen these kinds of things before, so certainly we've seen divisive clustering, and we looked at a graph of nodes in a social network. With Girvan-Newman clustering, the process here was to evaluate the betweenness centrality of every edge in the graph, and iteratively remove those edges to start breaking up the cluster. So we start with a huge cluster where originally all nodes are in the same cluster, and we remove these edges iteratively, evaluate some metric, here we use modularity, and say as the number of edges we remove changes the modularity, we look for some point where our metric is maximized, our quality or clustering quality metric is maximized, and we say that's the set of clusters we have. Alternatively, there's the point assignment method. A number of different community detection algorithms work this way, where you start off with a number of different clusters, and you add points to the cluster that they're closest to, or can do this sort of point assignment. The most popular sort of point assignment method that we'll talk about is k-means. We'll talk about that next time. So first, we'll talk about agglomerative clustering. The key idea here is to repeatedly combine the nearest clusters. So at every run through or every pass through our data, we'll identify two clusters that are closest to each other, merge those two clusters, and then repeat the process. So to do this, we have three questions that we need to answer. First is, how do we represent a cluster if it has more than one point? So a cluster of only one point, it's just one point, right? So you can treat that cluster and that point interchangeably. But once we start adding points to a particular cluster, then how do we represent perhaps the center of that cluster? Question 2, how do we determine the nearness of two clusters? We've talked about distance and similarity metrics. How do we apply those techniques or ideas to this context of clusters now that we have some way to represent clusters? And then finally, when do we stop combining clusters? So specifically, when we talk about agglomerative clustering, this idea is to repeatedly combine two nearest clusters, and we can continue to do that until we've combined all clusters into one. But maybe that's not useful if we end up with just one clustering. So how do we know when we should stop? So let's answer the first question about how we represent a cluster of multiple points. So the key problem here is when we start bringing or combining points into the same quote-unquote cluster, we need to figure out or represent the location of each cluster. Now that a cluster has multiple points in it. So here, what is the location of that cluster? And we need that information because we have to evaluate the distance between this cluster and other points, or this cluster and some other cluster. What is the position of this particular cluster? If we go back to your standard kind of geometry where we have some Euclidean space, then what we can do is talk about this cluster having a centroid, which is some central point. So in the Euclidean case, we can do this just by averaging all the data points, and then we get some centered mass or centered point in this particular cluster. And that makes sense for the Euclidean case. But in the non-Euclidean case, where we're talking about maybe cosine distance, or we're talking about Jacquard similarity or Jacquard distance, or something like that, then the Euclidean case starts to break down because we can't really talk about averaging anymore. So if we talk about 2 points and their cosine distance between them, we're no longer talking about, what is the average point between them. We have to somehow say, well, what is the average angle between them? So then we start to lose this idea of some average point. So instead, we have to focus on the idea of particular points. The only locations we have are the points themselves. So averaging doesn't make sense here. So then we can introduce the notion of a clustroid, not a centroid, where a centroid is this created point that is this average of multiple points. We can't do that in the non-Euclidean space. So instead we look at a clustroid, which is a pre-existing data point in the data set that we think is at least the closest to or can represent the center of this particular cluster. So ideally, this clustroid is some point in our data set that is closest to all other points in that cluster. So intuitively, this idea of a clustroid makes sense. We can't evaluate an average point, but we can select a particular point from our data to represent this cluster. We want to select this point in an intelligent way. We do so by saying the clustroid should be the point that's closest to all other points in this particular cluster. But then we have to wrestle with another question of what does it mean to have a closest or a point that is closest to all other points. One method is you look at the clustroid and its distance to all other points in the cluster, and you want to minimize the maximum distance. No individual point should be very far away from the clustroid. Or alternatively, you could say, well, the overall average distance among all other points in the cluster to the clustroid should be low. Or you can do the sum of squares or some other weighting mechanic, but critically, you need to define or determine what you want to use as your closest metric, sort of based on your context. So again, what is the appropriate way to do this? It really depends. In the same way that when we talked about centrality metrics, it depends on what your context is. So if you want to make sure that your clusters are all tight, then maybe you want to make sure that you want to prioritize the maximum distance from the clustroid to any other point. If you want to make sure that your clusters are evenly spread, you want to prioritize the average distance. So what makes sense for your particular case? That gives us a way to represent clusters. So we can represent clusters as their centroids or as their clustroids, either using some created summary point or having intelligently selected some point from the data. How do we evaluate distances between clusters now? So we can evaluate distances between points, no problem. What does it mean when we want to talk about distances between pairs of clusters? Because ultimately, we have the second question. When we look at iteratively combining clusters, eventually we'll have to combine not one point with one cluster, but two clusters together. So how do we know which two clusters are the most similar? Again, there's some intuitive answer here. We can just look at the distances between the centroids or the clustroids of a given pair of clusters. So if we think of clusters as being essentially points that are represented by exemplars, the centroids or clustroids, then we just evaluate distances between those and continue as though we're only dealing with points. Alternatively, you could look at other approaches or other metrics here like intercluster distance. For approach one, where we're just looking at distances between example points, it's a relatively straightforward question. We can go through this as an example. So here are a bunch of data points in a 2D Euclidean space. What are the two closest points? These 2 points in blue. We can generate a centroid here by taking their average. Next step up, we look for the next closest set of points. So these 2 green ones, their average here. Now we have a new centroid for this cluster. And now we need to start to compare points and clusters. So we'll see here on the left, the point at the origin, and this centroid of 1.5 and 1.5. Those are the closest. So now we have to come up with a new centroid for that. So we look at what is the central point for all 3 points in this cluster. And we can keep doing this without end until we've either clustered everything or we reach some stopping condition. And in fact, these hierarchies of clusters are useful if we're talking about doing topic modeling. These might be nested subtopics. So this sort of embedding is a valuable thing. But looking at distances between summarized or exemplary points between clusters isn't the only way to generate this dendrogram. You could also look for ways that are going to be more robust. So one of the issues you may have with looking at these averages, especially if you're looking in the Euclidean space, you could very easily be influenced by outliers. So the nice thing about the clustroid approach is that you're at least looking at medians, which are going to be slightly more robust to outliers. But maybe you want to make sure that it's not just my closeness to a single point in my cluster that determines whether I should do these merges, but I want to look at the overall distance or the average distance between all pairs of points in these 2 clusters. And you pay a penalty for that in terms of computation, but in the end, you potentially have a better or more evenly distributed or higher quality clustering approach with this idea of intercluster distance. We want to minimize the distance between any 2 points within a cluster or within a pair of clusters that we want to merge. One of the last thing we'll talk about is how do we know when we want to stop combining clusters? So especially in this agglomerative case where we move up this hierarchy of clustering, when do we stop? Because as I mentioned, even if you have a relatively complex dendrogram like this, at the end, if you just go until all clusters are together, that's potentially not a useful clustering, because you could have just known that beforehand. So really what's interesting about the dendrogram here, or this clustering, are these intermediate steps. So how do we know when to stop in these intermediate steps? And there are two real approaches to doing this, to identifying what's called the termination condition. So the first one is essentially by fiat. I specify some k value that says, well, I want to continue clustering until I reach some pre-specified number of clusters. Alternatively, I could look at optimization. So I want to, as I remove cluster, or as I merge clusters, I want to evaluate some metric and stop merging clusters when some metric changes in some significant way. Now, which one you choose, as in all cases, is dependent upon your context or what you're trying to do. So for instance, maybe you know from domain knowledge, how many genres are there, and you're looking at books or documents. So you know from just the domain, well, we can't have more than the number of genres in books if we're trying to cluster books. Or if we're doing political parties, maybe we just know how many political parties there are in a country, and as a result, we can specify, well, we're trying to cluster into political parties, so we specify this k value from beforehand. Another example is looking at different kinds of celestial objects, comparing galaxies and quasars. Well, if you're not a galaxy, you're a quasar, so the k value here is 2 just by the domain. And there are other ways you could get this from domain knowledge or some restriction in your data, restriction in your context. Optimization-wise, though, we've already seen this idea of optimization come up with the Girvan-Newman case, where we didn't specify a k value beforehand. Instead, what we did was we said, well, here's some metric that we want to optimize, specifically modularity in this case, and we will iteratively remove these edges until we've maximized our modularity metric. So then we say our k value is whatever the number of edges, or whatever the number of clusters or communities that we've identified after we remove this many edges. Ultimately, though, you still have to pick something. So in the case of the pre-specified k, you have to pick k. In the case of optimization, where you allow the optimization to pick your k for you, you still have to choose some metric that you want to optimize for. Whether that be modularity, or whether that be some intercluster distance, or something else, you have to choose that too. So modularity works well as a metric to evaluate quality for clusterings in the graph case, but here let's talk about a more general sort of evaluation or metric for termination called cohesion. So here, when we talk about cohesion, which can have a number of different interpretations, which we'll talk about in a minute, there are two general ways you may optimize for cohesion. The first is to merge or continue to merge two clusters in your data until the overall metric is maximized. And look for the maximal point or the minimal point for your metric in this sort of global optimization case. So you want to select some set of clusterings or continue to do this merging until you are sure that you are at the maximum value for a particular metric. Now, in contrast, you can do a more simplistic sort of threshold-based approach, where if you take two candidate clusters that you want to merge, you can merge them together, evaluate their cohesion, and say, well, does the cohesion of this new cluster that I've created, is it above or below some threshold? If it's below some threshold, then you just stop here and say, well, we're done, that's the end, we're not going to merge anymore, which gives us a different view of the space of the cohesion metric, because maybe we are stopping early or stopping potentially too early, where if we allowed this to continue, we may have ended up with some overall better clustering, but we have specified some threshold that forces us to stop early. Now, you pay trade-offs here in terms of computation time and how many iterations you want to go through. But again, how you want to do this is dependent upon your context. So we'll talk about a number of different ways that we can define cohesion. So one way we could optimize for cohesion is via diameter, where we define diameter to be the maximum distance between any 2 points in the cluster. In the same way we define diameter for graphs, where we defined it as what is the longest, shortest path in our graph. That's the diameter for the graph. Here we do the same thing for our cluster, and when we want to optimize for cohesion, we try and minimize this maximum distance. We look at all pairs and find the maximum distance among all pairs in this cluster, and we want to minimize that value. But that has us look at all pairs in the cluster. Alternatively, we can optimize cohesion via the radius. We define the radius as the maximum distance between the centroid of a particular cluster and all the points in that cluster, which gives us some cost savings in terms of computation time, because now we don't have to look at all pairs. We only have to look at all singular points in this cluster and compare that individual point to the clusteroid or centroid of this cluster. And then once we have taken this maximum, or once we've scanned through all these distances, we just take the maximum distance here and then minimize it. Alternatively, we can look at aggregations, and rather than taking the maximum or the minimum value here, we can look at averaging across these distances. So another metric we'll introduce is this idea of average distance, where we look at all pairs again, as we did with the diameter, but instead of taking the maximum, we just take the average. So we could have a couple of pairs that are very far away, or a few points that are very far away, but as long as our most of our points are like tightly clustered together, that's fine. The last cohesion metric we'll talk about is density, where we define density as the ratio of the diameter of the cluster. So what's the maximum point, the maximum distance between any 2 points in the set, or in any 2 points in this cluster, over the number of points in the cluster in total. So ideally you want these tightly packed clusters that have many points in them, and the maximum distance between any 2 points is small. So these are a few different ways that we might optimize for cohesion, but that leaves us with the next question of how do we actually implement all of this? Because clearly when we talk about comparing diameter and radius, we have to pay different costs in terms of computation. For diameter, we have to evaluate distance among all pairs of points in a cluster, whereas for radius, we only have to evaluate distance between the centroid point or the central point, and then all other points. So we only have to do that with linear and the number of points in that cluster. So clearly there's some differences here when we want to talk about implementation. But if we look more generally, then essentially at each step of the hierarchical clustering, this agglomerative clustering approach, we need to compute pairwise distances between all pairs of clusters and then figure out which one do we need to merge. And from a complexity standpoint, this is cubic in our number of nodes, which is definitely not the kind of complexity we want. And we've already been talking about how quadratic in our space for just generating the distance matrix at all is potentially too computationally intensive. Now, through careful implementation of this, we can reduce this complexity down to n squared log n, which is still going to be potentially too large. Again, we talked about n squared just by itself being too large, and while we have a pretty substantial savings from n cubed to n squared log n, it's potentially still too much for really big data sets that we can't necessarily fit into memory. So how we'll deal with this is through k-means and some of the related optimizations for this, where we don't necessarily have to evaluate or keep all the information about hierarchies. We can do instead the point assignment approach and take advantage of some heuristics to optimize this kind of point optimization and do these clusterings faster at the expense of potentially generating less information, since we no longer keep the hierarchy information. But there are many other kinds of approaches for doing clustering. So this is a visualization of different clustering approaches applied to methods that are available in scikit-learn and how long it takes. And you can see for k-means on the left, if you have already well-separated clusters, k-means works decently well. Or you might have these sort of weird shapes where some other approach like dbScan is more appropriate. And in fact, you can go to the scikit-learn clustering page, and you can see a number of the different methods that they list for clustering, and some good insights into when they're useful, how they're parameterized, what distance metrics they use, and whether the distance metrics they use can be changed. So that isn't to say that we've addressed all the issues or interesting problems in clustering. For one, we've assumed essentially that all points exist in exactly one cluster. Now, let's abstract away the hierarchical clustering aspect and how a point can exist in multiple clusters up the hierarchy, because that's not quite what we're going to talk about here. Instead, there's a different idea where some points should exist or are very clearly in one cluster, and only one cluster. But there are some other points where they could exist in multiple clusters. And you could easily think of contexts where that makes sense. So the social context, where you exist in one cluster of your family, you also exist in one cluster of your work social group, another cluster in your school social group. You can imagine if you're looking at influencers or influential people who have expertise across a number of different subjects and you're trying to do clustering based on topic. Some people talk about multiple topics. So how do you represent that? And there's an area of clustering that looks at this idea of fuzzy clustering. Same thing goes for graph analysis or community analysis, where you can have points that exist in multiple communities. So there's a whole area of this that we have not talked on. But if you have questions or interest in this kind of approach or the idea of fuzzy clustering, or you want to use that in your project, by all means reach out. The main issue is when you relax this constraint that a point exists in exactly one cluster, you introduce a lot more complexity into the system, because now you have to evaluate potentially all pairs at all times. You can't throw away points once you've dealt with them, in the way that if all points only existed in one cluster, once you've evaluated or assigned a point to a cluster, maybe all you have to keep track of for that cluster is its central point. You no longer have to care anymore. Whereas in the fuzzy clustering case, you always have to keep track of all points. So there's a lot more complexity that you'd have to deal with here. But for now, we'll end it there, where we've talked about different ways for doing hierarchical clustering, some of the problems therein, how we identify or represent clusters of aggregations of points, how we evaluate distances between these aggregations of points that we call clusters, and when we might want to stop clustering based on different methods of identifying the number of clusters or optimizing for a particular metric. So next week we'll talk about k-means. If you have any questions about what we've talked about or discussed in terms of hierarchical clustering, feel free to post in the discussion forum.